this video, we're going to look at the second derivative to describe concavity of a function and look at the second derivative test. So first of all, remember our derivative describes the direction of the line. So does it increase, decrease? The second derivative describes concavity of the original. If you look at him as the first derivative of the derivative, then it can tell you if the derivative is increasing or decreasing. But if you look at it compared to the original, it will tell you concavity. And concavity is just the bend in the curve. So when it's concave up, it's opening upward. And when it's concave down, it's opening down. So if our second derivative is negative, that means it's concave down. If it's positive, that means it's concave up. A point of inflection is similar to a critical, except that the concavity has to change. So we find it in the same way, except that we use a second derivative, and there is a typo here. Possible points of inflection are going to be whenever the second derivative is 0, or when the second derivative does not exist. The typo here that should have said f prime is not differentiable. So if I want to determine concavity on an open interval, I'm going to use my sign pattern test again. First, I have to find when the sign can change, and that's going to be when the second derivative is 0 or doesn't exist. And then we determine the sign at one test value, just like we did before. So when we find our second derivative here, we're going to first get x squared minus 1, and then our second derivative is just going to be 2x. Concavity can change when this equals 0 or when it doesn't exist. So x equals 0 is a possible point of inflection. So on our sign pattern test, we're going to plug in 0. And I want to choose a test value before 0. And we're plugging it into the second derivative this time because we're looking for concavity. So if I plug negative 1 in right here to my second derivative, I get a negative. And here I'll plug in positive 1 and I'll get a positive. So the way we answer this is everywhere on this interval, so from negative infinity to 0, my graph is concave down. And then here from 0 to infinity, it's concave up. So we can also use the second derivative to determine if a critical number produces a min or a max. So just remember that relative extrema have to occur at critical points. So once we find those critical points, then we can determine the concavity at each of those points to determine if it's a max or a min. And what that means is, let's say I found a critical point. So right here I know that it's going to be a max, a min, or neither. If I know that it has to open downward, there's only one option. It's got to be a maximum. If I find a different critical point here, and I know it's got to open upward, then I know we had to have produced a relative minimum. And if nothing happens, then there is neither a min nor a max. So we find criticals, and then we plug them into the second derivative to determine if they're maxes or mins. So here it says use the second derivative test. A lot of times the second derivative test is easier because our functions are like 1 degree less. In this case, we kind of have big numbers, but that's okay. So our first derivative is negative 15 x to the 4th plus 15 x squared. I do have to find critical points because that's where all relative extrema are found. So I do need to set this guy equal to 0. I'm going to factor out a negative 15 x squared so that I get positive x squared minus 1. And then my critical points here are going to be x equals 0 and x equals plus or minus 1. And these are the locations of my maxes and mins. Now I can use the second derivative to determine what happens at each of those points. So my second derivative here is going to be negative 60 x to the 3rd plus 30x. And if I write that in factored form, I'm going to go ahead and factor out a negative 30x so that I get 2x squared, and then I'll get minus 1. And I wrote it in factored form because remember, all we need is the sign. So I'm going to evaluate the sign at each of our critical points to determine concavity. So when I plug in 0, here I'll get 0 times a negative number, which is just 0. If That means here we have neither a max nor a min. Then I'm going to plug in my other two, and when I plug in positive 1, I'm going to get a negative number times a positive number. Positive 1. Okay, so I get a negative. Just double checking my work here. So since it's negative, and that's the second derivative, that means it's concave down. And you can see from my illustrations, that means we must have a relative max at that critical point. And we're going to do the same thing with negative 1. So when I plug in a negative 1, I get a positive times a positive, which in this case means it's concave up. So if it opens upward, this must have been a relative minimum. And so in summary, our first derivative tells me where the original is increasing and decreasing. Criticals are going to be when we set it equal to 0 and does not exist. Our second derivative discusses concavity. A point of inflection is when concavity changes. It's possible when the second derivative is 0 or doesn't exist, but we do have to verify that concavity actually changes. And so this down here should be review, and that's it.